And thank Jay for being the reason for why we're all here, and happy birthday, Jay. It's Jay's 60th birthday, if anyone missed it. Which brings me to today's topic, which is wrinkles. Because it's a mechanical instability. So maybe you saw in the previous slide, my talk was about Smectic order of wrinkles. So I'm going to somehow connect wrinkles and liquid crystals. But let me first of all describe what I mean by wrinkles. I guess you all know that, but let me just be on the same page here. So if we take a very thin elastic sheet and we put it on a soft substrate, it can be a liquid, it can be a much softer solid, and then we compress it from the sides, then typically it wrinkles. Okay, it wrinkles at some finite wavelength. I'm going to talk about this in a minute. And if you further compress it, then you know there are some nonlinearities. Typically in the liquid it will make a big fold, in a solid it will make some kind of a period doubling. But in today's talk I'm going to talk about this linear regime in which we get wrinkles at this finite wavelength. Now everything gets more complicated if you make more complicated boundary conditions or things like that. If you do not maintain this uniaxial, this one-dimensional symmetry. So for example, if now one is to compress the sheet in the perpendicular direction, then typically we get these zigzag or herringbone patterns, and making all kinds of boundary conditions or compressions gives us very rich zoo of patterns. One can, for example, this is a flat sheet lying on water, and then Paulson et al. In Amherst at the time, they poke it in the middle, and it develops these radial wrinkles and so on. Now, we don't really need external forcing or boundary conditions, special boundary conditions to create those wrinkles. They can emerge spontaneously as a result of geometric incompatibility. So imagine non-flat, let's say spherical shell. We put it on water, which is flat, like on a flat bath. And then one lets water wet the entire bottom surface of the sheet. Okay, so because of, let's say, liquid air surface tension is big enough for the entire bottom surface of the sheet to wet, and then it has two options. Either it can remain spherical, in which case it displaces a lot of water, okay, or it has to flatten somehow and get closer to the plane. So let me show you a movie of what happens. This was taken by my collaborator Octavio Alboran in the Max Planck Institute for Dynamics and Self-Organization. Takes a little while for a sheet to wet, and eventually when everything wets, it reaches an equilibrium with some wrinkled pattern in the center. This sheet is PDMS. It's a few centimeters big and like tens of microns thick. Okay, so one gets this nice wrinkled pattern as a result of the geometric incompatibility. Similarly, one can take a flat sheet, elastic sheet, put it on a spherical droplet. Again, everything here is small, so surface tension wants to make the sheet, the droplet spherical. And again, as a result of geometric incompatibility, we have wrinkles around the sides, and one can explain these two phenomena, at least very coarsely, from just geometric principles. There is some mismatch between the natural geometry, G bar as Effie called it, of the sheet and the geometry of the surface on which we confine it. This results in excess area or excess length of the material. Here it's around the center, here it's around the sides. And this excess length is accommodated in the form of wrinkles, just like in the uniaxial case. Now, let me talk a little bit about liquid crystals in order to explain to you why these are the same. So, liquid crystals are basically rod-like molecules living inside some solution. And the simplest phase, okay, we'll find it in high temperatures, low densities, is the isotropic state. All the molecules are free to move around like in a liquid. And they're also oriented randomly, okay, or there are no long-range correlations in the orientation of the molecules. If one is to take this system and cool it down a little bit, it might undergo transformation to a nematic state, in which the locations of the molecules are still behave like a liquid, okay, they're random and they move around. It's not crystalline in any way. However, the orientations of the molecules have long-range order, okay? Locally, they want to align in the same direction. So this is called nematic state. And if one further cools this system down, it will undergo transformation to a smectic state, in which the molecules also get arranged in layers. So the nematic direction is perpendicular to the layers. This is a smectic A state. But the positions of the molecules are no longer homogeneous in space. So the ground state of this smectic phase, which I'm going to talk about today, is basically a density which behaves like a plane wave. Okay, there is degeneracy in those ground states. That plane wave can be in any direction. It can have any phase. Only the magnitude of the wave number is set by the molecular size. So it's a fixed wavelength, but it can be in any direction with any phase. This is the ground state manifold. Now, if we want to get to write the state of a smectic liquid crystal more generally, we can just replace this phase with a general phase field. So we replace the phase with a general phase field, and then we are no longer in the ground state, so we pay energy for different things. And at least deep inside the smectic phase, when the smectic is really perpendicular to the nematic director, we remain with the two main contributions. One of them is a compression term, which penalizes the layers from having the wrong spacing. So there is a preferred spacing set by molecular size. And there is also a curvature term. Here I write in linearized form the Laplacian. You can often it is written in terms of the mean curvature of the layers, which penalizes the layers not being flat, but rather being bent. Okay? So this is generally a very standard model for a smectic liquid crystal. And it's actually used not only for smectic liquid crystals, but also for many other liquid or liquid crystalline systems. For example, all of these, diblock copolymers, amphiphils, domains in ferromagnetic material, Rayleigh Barnard cells. So basically, models that look like this or almost exactly like this are used in all of those systems, and they describe basically these main two energetic contributions, which penalize the wrong layer spacing and penalize the curvature of layers. And now I want to convince you that the same thing exists in wrinkles, and this helps us explain some of the characteristics that we see in wrinkled patterns. So yeah, this is the diplock pictures I showed in the previous slide. Again, this is liquid. Okay, there is nothing solid here. There is no G-bar. There is no reference metric or excess length or things like that. And this is the zigzag wrinkled patterns, which made by compressing an elastic sheet on a soft substrate. These are different length scales, and still they look quite similar. And I'm going to try to explain why. So let me give you at least an intuitive explanation here. So let's say we have the sheet is locally compressed in some direction. I have some excess length I want to accommodate while trying not to deform a substrate too much. Okay? So again, imagine this is a thin elastic sheet. on a soft substrate. You can imagine either liquid or solid. Let's say liquid, and it has to accommodate some excess length. It can do it in the form of very fine corrugations. Okay, so this sheet is actually, of course, longer, right, than its projection. Now this doesn't deform the substrate much. Okay, it remains close to the plane. However, it costs a lot of elastic bending. Sheet is very bent. Okay, and this costs a lot of elastic energy. On the other hand, it can make like this one big buckle or few big buckles or very coarse wrinkles, in which case, in order to absorb a certain excess length, it has to deform the substrate significantly. So there is very low bending energy here, but the substrate deforms a lot, which also costs energy, let's say gravitational energy in the case of a liquid. So between those two, there is some preferred wave number. It's set simply by the ratio between the substrate deformation modulus, or the gravity, and between the bending modulus of the elastic sheet. These two give us length scale. So this is a preferred wavelength for wrinkles, and this is known in one-dimensional systems for many decades. You know, it's been generalized for two-dimensional systems and for cases in which there is lateral tension along the wrinkles and other cases. And there is one other feature that's basically different when we were talking about systems which are not one-dimensional in nature. And this is the case when wrinkles might be bent. Okay, wrinkles change their direction inside the plane. And there is a fundamental difference between this and the straight wrinkles that people studied a lot, where in straight wrinkles at every, I'm not sure if you can see this, so you can look at the screens on the side. Straight wrinkles have a flat principal direction at every point, okay, because of the symmetry. However, bent wrinkles have points in which there are two non-zero principal curvatures. And as most people here probably know, this implies Gaussian curvature, the product of the two principal curvatures. So if I look at the Gaussian curvature, here it's zero everywhere, but when I have a pattern of bent wrinkles, I have oscillating Gaussian curvature. As I go across the wrinkles, it becomes positive, negative, positive, negative. Now, there is a remarkable theorem by Gauss that says that this Gaussian curvature field is determined only by distances within the sheet. Okay, so I don't need to know how much the sheet is actually bent at every point in order to calculate this Gaussian curvature. It's only a function of the distances within the sheet. Okay, so if I have a sheet which is, let's say, naturally like a big sphere or something, it doesn't have length scale as short as these wrinkles. However, in reality, it is in the shape of wrinkles which has oscillating Gaussian curvature. It also means that there is oscillating strain. Okay, the sheet is actually, if I go across the wrinkles, stretch, compressed, stretch, compressed. Yes, so this costs elastic stretching. Okay, so unlike straight wrinkles, bent wrinkles cost not only bending energy and energy of deforming the material, but also stretching energy. The sheet itself is locally stretched or compressed laterally. For a thin sheet, this costs a lot of energy. Okay, now when I take these contributions, there is this contribution from elastic bending and from the substrate deformation, and which penalizes having the wrong layer spacing. And I have this contribution from elastic stretching, which penalizes curvature of wrinkles. Together, you know, I can Taylor expand it around the minimum, and it would look like what I call the Smectic energy function. There is penalty for the wrong spacing. There is penalty for wrinkle curvature. So in this sense, this gives the wrinkled pattern properties of a Smectic liquid crystal, okay, or other lamellar systems. Now, this can be done more rigorously. We can write the full energy of the system, so composed of elastic stretching term and elastic bending term, in the spirit of the works of Effie and Raz and Aran. So the elastic stretching penalizes deviations of the metric from a reference metric. Bending penalizes deviation of the curvature tensor from a reference curvature tensor. And there is some penalty for deforming the substrate. What I wrote here is for a liquid substrate, it simply deforms the deviations from the plane. Now, if I'm looking at the configuration which describes a wrinkled pattern, okay, then this metric tensor G, the curvature tensor B, and the normal displacement, they are all oscillating at the wrinkle scale typically. Okay, so this means that the entire integrand here oscillates at the wrinkle scale. Now, in many systems, I have scale separation. Okay, I know the typical wrinkle scale. Again, it's square root of it's k b over k to the power of quarter. Okay, and the system scales can be many orders of magnitude above this. The typical length scales in the target metric, okay, the radius of curvature of my big sphere, can be much above this wrinkle scale. And there's a scale separation, which allows me to take this energy density, which is quickly oscillating, okay, and just coarse grain it at the wrinkle scale. So I coarse grain this fast wavelength of the wrinkle scale, and I'm left with all the long wavelength dependence of the energy density. So how it's done? We make an ansatz, okay, for configuration. We write in terms of an amplitude field and the phase field, so that the z component of the configuration is amplitude times cosine of the phase. I'm not writing the x and y components. There are small corrections that basically it's a coordinate choice that we make to make everything a little simple mathematically. And then we assume slowly varying envelope. Basically, we assume that the amplitude and the wave number are both changing slowly with respect to the scale of a single wavelength. And then we just coarse grain our entire energy density at this scale. I will not take you through the details. Let me jump to the final result. We end up with energy density which look like this. This is already in a dimensionless form. And we can see that there is an elastic type, an elastic energy component in the energy density, which basically it's identical to regular elastic stretching. However, it doesn't see the actual metric anymore, which has all the intrinsic structure of the wrinkles. It only has the coarse-grained metric, which is this metric smoothened over the scale of a wrinkle. Okay, so it doesn't see the internal structure of the wrinkles, only the long scale excess length that is absorbed in those wrinkles. And so there is an elastic penalty for this deviating from an effective G bar, which is some small correction to the reference metric G bar. And all the intrinsic structure of the wrinkles is absorbed in these two Smectic terms. Okay, the term which penalizes the wrong layer spacing and the term which penalizes Smectic bending, which are, as I described before, only now we have the exact form of the moduli and the exact form of those terms, which are slightly different than normal Smectic, at least the curvature term, but are similar in spirit. So what can we learn from this? Okay, okay, it's all nice, some analogy. Can we use it to predict some characteristics of these patterns? So let me go back to the domain, breaking into domains like in the zigzag patterns I showed you before, and we can ask ourselves, okay, so typically we see the system breaks into these domains of straight and parallel wrinkles, which are separated by these domain walls. We can ask ourselves, how wide are these domain walls? And in liquid crystal theory, it's a textbook problem. The answer is given in terms of the ratio between the two Smectic moduli, the one that penalizes bending and the one that penalizes the wrong spacing. And we have those moduli, okay, because we arrived at them when we coarse-grained our energy density. So basically, we have a prediction for how wide these domain walls should be. And we test this with simulations. So these are finite element simulations, just regular finite element simulations of an elastic sheet on a liquid substrate, done by my collaborator Desi Todorova from Penn. And this is a top view, okay? It's a square piece cut out of a spherical shell, just like the video showed you in the beginning, maybe slightly different parameters. And this is a top view, and the color is simply the z displacement. And we can go to these. So in these parameters, it splits into 4 domains. Okay, we can go to domain walls and measure the width of the domain walls and test them again our prediction. And this is our prediction, okay, the dashed line, and these are the results. There are no fitted parameters here. So we get the width of domain walls. As you can probably see, there are many dots here that don't fit on our prediction, and one can ask why. And the reason is, to answer this, we need to not only, take a domain wall and fit it into an arctangent or something. We need to actually look at it. And we see that these predictions that sit nicely these domain walls that sit nicely on our prediction actually remain smooth, okay? If one follows the angle, it changes monotonously from one side to another. However, if we look at these large amplitude, basically, domain walls, one can see that there is some nonlinearity here. Basically, the domain wall, the wrinkle breaks into a pair of decones on each wrinkle across the domain wall. And this breaks our assumptions, okay, of the slowly varying envelope for the amplitude and wavelength. So our prediction doesn't work here. And these are actually, this gives, at large amplitude, domain walls at a fixed fraction of the wavelength. Now, this is somewhat similar to nonlinearities also in die blocks and so on. Our theory cannot really predict it precisely, but it's reminiscent also for some reason to nonlinearities in those liquid systems. We can go on to calculate the typical size of domains. Okay? So as I explained, in each domain, the wrinkles are straight and parallel, okay, so it means that within each domain, the Gaussian curvature is more or less 0. So we can think about these domains as just Euclidean patches with which you are trying to approximate the spherical target metric of our shell, okay? So this is similar, for example, for trying to estimate a sphere with a geodome, with Euclidean patches. Now we have, as I said, 2 energy components in our coarse-grained energy density. There is the elastic term, which penalizes deviation of this coarse-grained metric from the target metric of a sphere. So it would like domains to be as small as possible, okay, for this geometric fit to be as good as possible, okay? However, there is a Smectic term which penalizes domain walls. So in the previous slide, I talked about how wide domain walls are, but we can also get from Smectic liquid crystal theory how much energy domain walls cost, okay? Now, so those, by the way, those 4 simulations are done at different thicknesses. Otherwise, they are the same. They are also hexagons cut out of a sphere. And these 2 components, the elastic component, which likes small domains, and the Smectic components, which likes large domains or fewer domain walls, they compete. And they give us this prediction for the scaling of the typical domain size. It depends on the total curvature in our patch and also on the Foppel-von number or the thickness, both to very small powers. But in simulation, we can change the thickness by a few orders of magnitude. So, and we can at least qualitatively, I'm sorry, say that the typical domain size scales more or less in a correct way with our prediction for the typical domain size in those systems. Yeah, okay, I should wrap up, so let me skip that part. And I'll just summarize. So basically this gives us, you know, prediction for a few characteristics of those wrinkled patterns. However, it also gives us a way to efficiently simulate wrinkles, at least in those systems which have this scale separation. Because in the simulations I showed you here, there are very standard simulations of an elastic sheet. In order to capture the shape of all those wrinkles, we need at least a few elements within each wrinkle, right, to capture its shape. However, in this coarse-grained view, okay, when we write the energy in terms of amplitude field and phase field, which are changing slowly, we can use elements which are a few wrinkles big or many wrinkles big, depends on our scale separation. So this opens the door at least for a very efficient simulation of wrinkled patterns. And maybe this can also open the door for trying to solve the inverse problem, to tune the shell geometry or the boundary conditions to give us the pattern that we want. Okay, so let's say we want a wrinkled pattern in the shape of J's face, let's say. We can come up with this weird looking sheet, which when will be put on water will give us the wrinkled pattern that we want. Okay, so this is a bit of the future, but this is about it. I would like to thank my collaborators here. You can watch this movie and read our paper, and that's about it.